Welcome to finding the center of mass for a planar lamina. Alright, this probably has some good, useful physics types of applications. A planar lamina is just essentially like a, I can copy that picture out of the book, but it's sort of like a thin type of sheet. Now, it represented by a density function, meaning it could be denser in other spots of it, other locations on the sheet, than some places more dense than others, so that would affect the location of the center of mass. But the way you calculate the mass across some region is you have a given density function, and you evaluate the double integral of that density function across whatever regions being defined. So that's a variable density. There's probably some sort of, I guess if it's fixed density, I guess it's just some probably physics formula or something. Now, anytime something's variable, kind of like calculus, you may have studied, for I'll give you an example, talking about being variable or not, or in your earlier calculus studies, you might have like work done by compressing or stretching a spring, or any kind of work done by a variable force, where the force is not the constant across the distance, then it requires integration. Obviously, if it's constant force times distance would just be your work if it's the same force. Well, anyway, back to this now. So we have to. So there's three things you have to calculate that lead you to the center of mass. First of all is the mass. Then you have these two moments of mass. These formulas are on my formula sheets. You don't have to memorize them. But just be careful that you look at them correctly when you're using them. Using the mx moment is actually a double integral across the region of integration. And speaking of which, is once you actually you get the region of integration correct, it will be the same for all three of these double integrals. You'd never have to change that. So once you have it once, you've got it. But then you're integrating y times your density function, and then for the my moment, you're evaluating x times your density function, and then to get the center of mass, often written as x bar, y bar, the x component will be my divided by m, and then your y component would be mx divided by m. That might not seem completely logical to you, and that's fine if it doesn't. Just follow this, though. Follow that formula. The center mass, also known as the centroid of a region. Okay, let's see some of my earlier calculus notes. I don't know if I do have in Cal 3 or not, maybe, but Stewie appears a lot in Cal 1 and Cal 2. So whenever he barks out some instruction, it's got to be something pretty serious there. Yeah, so the center of mass must be located in your shaded region of integration. So that's something you could look at when you were done if you wanted to. In other words, if you, like say, if you graph this region and then you get your center of mass and try to see that it falls in that shaded region somewhere. Of course, where it falls is going to depend upon the density function. But the fact that, so let's just say, I'll pick an easy number. Let's say you got a center of mass of 3, 4. Well, 3, 4, well, it's going by 2s there. I guess my x-axis is going by 1s. Yeah, it's going by 1s here because 2 cubed would equal 8. Okay, so 3, 4 will be right there. Well, that could not possibly be my center of mass, aka centroid, because it's not in my region of integration. All right, so let's see what we got here. We've got a region bounded by y equals x cubed, y equals 0, x equals 2, and the density function rho is k times x. A lot of these problems I'm using k. I can't remember on exams if I use a k or not. If so, go with it. What happens is that with the k there, each of those individual calculations will have a k, but when you calculate the center of mass, those k's will be, you'll have my over m and mx over m. Those k's will cancel at that point. In the final answer. So, I could have a number there. I could just have like 6x instead of kx. But it's not uncommon to use some generic, multiplier like k. So we're going to find the center of mass and the center of mass. Let's look at the graph of this. So you see I have y equals x cubed, and we're bounded by x equals 2 and y equals 0. So that's pretty easy enough. And I'll go dy dx. Now I'm going to save some time in this video by just kind of skipping a lot of the routine calculations here, just to save us some time. But the setup's obviously very important. So there's the kx for the density function. So lower to upper, we're going 0 to x cubed, and then left to right, we're going 0 to 2. So this is really a pretty easy integral. You work this out, blah, blah, blah. You get 32k over 5. Would be the mass. Now, next thing I'm going to do is we're going to calculate the moments. The my moment, you automatically put an x in there and you multiply it by that same density function. It's still, you know, kx. The density function doesn't change in the same problem. So we've got x times that kx right there. So obviously the k is a constant, so it can be pulled out. So you're integrating now x squared dy dx, so that makes it x squared y. Pretty easy integral, bringing x cubed to x fifth, yada yada yada, easy, 64 over 6, which then reduces to 32k over 3. Now the mx moment, you put the y in there. So it's y times kx. The k can come out. And we're still, remember I said a minute ago, the limits of integration do not change once you have them set. So obviously each integral is going to be a little bit different. And they may yield the same answers by coincidence, but the work will be different. So now x integrate y, get 1/2 y squared. Okay, once again, this is not very complicated either. You end up with not a fraction. This time you get 16k. So to calculate your actual center of mass coordinate, your m is 32k over 5. We got that back up here first. That first thing we did right there. And your my moment, which actually goes in the x position, is 32k over 3. And then your mx moment right here is 16k. So if you divide those, like I was saying a few minutes ago, the k's will cancel. And that ends up reducing to 5/3 and 5/2. So what I did up here, just for the heck of it, was I just showed that 5/3, 5/2 is in my region. But that's not mandatory. But if you have already sketched your region of integration and you want to take a look at it, then you could see if it was there, you know, if it looks like it's in there or not. Okay, this stuff's not too bad. Obviously, it just depends on, you know, I don't want these double integrals to get too complicated, but by any means, because you have to do 3 of these double integrals, so that's already tedious enough. But it's just, yeah, as long as it doesn't get too involved, it's not that bad. This one looks maybe a little more. So what do we have here? Y equals x cubed, y equals 8, x equals 0. Actually, it's very similar to this last problem, isn't it? Let's see. X cubed. Yeah, so it's kind of like this top portion right there. All right, that's fair enough. Oh, this time I used a number. 6x. Instead of k, I used a number. Okay, so either way, it could be the k or it could have a number here. So I'm going to go dy dx. It's going to go from x cubed to 8, 0 to 2. Now, if you want to switch it to dx dy, you could, because that way that would give you a 0 on bottom. But then you have, if you don't mind having a cube root of y here, because you'd have to solve x equals the cube root of y. So it would go left to right. It would go from 0 to the cube root of y. So if you prefer that, go right ahead. I just wanted to keep it nice, positive integer exponents there. So, but you could make a good case for having a 0 down there at the bottom. Maybe I should have done that. Oh well. So I brought the 6 out, so you have then the antiderivative dy will just be y, so you have an 8 minus an x cubed with that x there, so you'd want to distribute this, of course, before you took the antiderivative. So you have 8x minus x to the 4th, and let's see, 2 easy power rules there with the 6 still sitting there. So we get 288 divided by 5 as the mass. Now, the my moment, see, I kind of put that x in there to show you, so it's x times 6x. So it makes that 6x squared, which you can toss a 6 out there, brings in a y, 8 minus x cubed. So this time we'll have x squared times 8 minus x cubed, 8x squared minus x to the 5th. Easy power rule, put in 2, put in 0. We have the 6 up front. So we have, ends up being exactly 64. All right, that's fine and dandy. And now we need the mx moment. So that puts the y in here. So we have 6xy, so bring the 6 out. Now this, so actually we have a y to integrate this time instead of just dy. So that's going to make it y squared over 2, so 6 over 2 would be 3. Y 8 squared is 64. X cubed squared is x to the 6th. Distribute the x. Power rule again with a 3 in front, 0 to 2. I get 288. So the x bar, y bar, the center of mass and centroid would be the 288 over 5 was the mass that we got at the beginning. 64 is the my moment. 288 is the mx moment we just got. So if you take those fractions, divide them, reduce them, you get 10/9 comma 5. That looks pretty good. Now, because the x-axis is scaled by 1s, even though it's 2s here. It's 1 on the x-axis, just like before. So 10 over 9 is just a little bit bigger than 1. And then there's 5 right there for right there. So that's in there. Remember, it doesn't have to be perfectly centered in there because it is dependent upon the density function, but it's in there, so that's good news. And there we go. So this is, as long as we can get the region of integration set up, and it's not too bad. I don't like for these integrals to be very complicated, strictly because you've got to do 3 of them to get the center of mass. So I don't want to burden you down with something. Well, how about this graph? Y equals 4 over x, y equals 0, x equals 1, x equals 4. And yeah, because that y equals 4 over x, that's never going to hit the x-axis. So and it's never going to hit the y-axis either. It's never going to touch either axis, so it kind of needs 2 boundaries in there for x to trap it off there. So 1 to 4. Yeah, so that's why I labeled that one as 1, so you can see that that's not the y-axis. All right, so, and then we have a k back in there, kx squared. So so let's look at it. So if we go, I'll go dy dx again. So it's going to go from 0 to 4 over x vertically, dy. Then x must be numerical, so it's going to go from 1 to 4. So we have, we'll see, bring out the k, you have x squared y, pretty easy work from here, I think. So let's see. And then distribute, integrate from 1 to 4, and you end up with 30k. So that's not too bad. Now, just to sort of, could use the word torture you or whatever, or just for practice, I threw this in there. Now, of course, you'd never want to do it this way, but this kind of, practices our skills of, reversing order of integration and that sort of thing, which is not applicable to this problem, but it's a good skill to know for test purposes. Would not give you a center of mass problem that required 3 pairs of double integrals like that. But what I did is, okay, so I kind of expanded the graph to show you, as we're all the way down to the axis there. See, this one, lower to upper is one graph, left to right is one. I mean, one doesn't change. But the reason why, if you went dx, dy, you have the same left value, which is 1, but you have 2 right values. The blue curve and the vertical line at 4. So it would have to be split right there where I have that red line into 2 pieces to where you have 2 different right functions. All right. I guess I worked that out to show you it was 30 Oh, yeah, I put in the x squared. I didn't put the k in there, so it worked out to be 30, which matches our 30k right there. I didn't put the k in there. So anyway, so for the bottom rectangle, see, that's a rectangle, so everything would be numerical. 1 to 4, 0 to 1. No variables, but we have a variable here. Left to right, you're going from 1 to 4 over y, because if y equals 4 over x, x would equal 4 over y. And then 1 to 4 again numerically. Would be, upper this time though, not left to right, upper. 1 and then 4 right there. This time it's scaled by 1s instead of 2s. Let's see, so it worked out to be 30. Okay, so that's just practice on reversing the order. So now I'd come down here, and we got to get the my moment. So there's our x we have to put in there times our density function kx squared. Obviously just toss that k out, work with it from there. X cubed y, so dy, so antiderivative dy is y. Put in 4 over x, put in a 0, distribute, you get 4x squared with the k sitting there. Not too bad. Go from there, easy. 84k, that's your my moment. Here's your mx moment. Would be y times that density function, so it's y times kx squared dy dx. So the integral of y dy would be 1/2 y squared, so I put the 1/2 on the outside with the k, y squared, put in 4 over x, and you actually get 16 over x squared, and 0 will be 0. X squared kills 16 over x squared. So and then 16 over 2 is 8, so the antiderivative of 8 dx would be 8x. With k there, 4 to 1 gives you 24k. So the masses are the denominators, 30k. The my moment right there is 84k. And the mx moment is 30k. And so we divide that, and we have 14 over 5 after you reduce it and cancel the k's. 14 over 5. Then we have 4 over 5 for the y of the centroid. So, and okay, I put a little dot there approximating about where it would be. It might not be perfect, but it's clearly in our region, so I'm very happy with that. Okay. Here's a mass, center of mass, that first quadrant. You see that graph does overlap, so we don't want that other region down there. So I only want the one that's in the first quadrant. Y equals 2x, y equals 2x cubed. You could probably get these points of intersection just by visualizing the graph, or however you want to get them. You don't have to solve them, but I solved them. Now the -1's coming from down there in quadrant 2 that we don't want. I mean quadrant 3. Obviously, when you solve that equation, you're going to get every possible point of intersection, but we only care about the 0 and the positive 1. So this one's kxy, so it's easy to set up. So we're going from lower to upper if I go dy dx, which would make sense. You don't want to take those two functions and solve them for x in terms of y unless you had to, in other words, to be able to integrate it. This by far is the easiest way. So you go from 2x cubed to 2x. And then left to right, you go from 0 to 1. So I'm going to kind of plow through this real quick. And like I said, this part's not too difficult. All right, so y dy, 1/2 y squared, k over 2 to the outside. Bring 2x squared is 4x squared. 2x quantity cubed squared is 4x to the 6th. Distribute the x through the parentheses. And then take the individual antiderivatives of those. 0 to 1, you get k over 4. So the mass will be k over 4. Now, so obviously for the my moment, we just put the x in there. Work out all this. Okay, blah, 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 blah. And you'll get 8k over 45. I don't think there's anything too complicated or strange in the integration there that I need to mention or discuss. I don't know why that 6 is so low. That kind of bugs me. That's all right. All right, so 8k over 45 is the my moment, so the mx moment means you put the y in there with kxy. And I have, okay, so it's still 2x cubed to 2x, 0 to 1. Nothing really weird here. You're just integrating y squared now. You want to multiply those two y's together, so you get 1/3 y cubed. So I brought the 3 out, put in the 2x and the 2x. Now they're cubed this time. And then time, okay, I skipped a step here. So 8x cubed times x makes 8x to the 4th. 8x to the 9th times x makes 8x to the 10th. Power rule for, I pulled the 8 out and did the power rule for both those without the 8. Got the k over 3, so it's 8k over 3. Put in 1 and 0, so it's 1 over 5. Yeah, 1 to anything being 1's quite convenient. 1 over 5 minus 1 over 11, that ends up being 6 over 55. Reduce, you get 16k over 55. So the mass is k over 4. 8k over 45 is the my. 16k over 55 that we just got is the mx. Divide them, flip it over. We get 32 over 45, and we get 64 over 55. I didn't really pinpoint that in there, but I will zoom in on this for a second. I guess I could try to squeak a little dot in there, I guess. 32 over 55 is oh, I could check. 32 over 45. Oh, that's around 0.7, roughly, and then about 1.1, 1.2 maybe. Somewhere between there. So about 0.7 right there, 1.1, 1.2. Yeah, it's going to be up in there somewhere. I believe it's in there. Okay. So like I said, you didn't have to check that, but I think we're okay with that center of mass. Now I think, before we leave center of mass here, we should certainly do one where we think it might be polar. So like I said before, when you think polar applies, use it. So we have y equals the square root of 9 minus x squared, which of course converts to the circle of x squared plus y squared equals 9. Now it tells us up here that we are in the first quadrant, so that's how we know our circle is restricted. And in rectangular coordinates, this integral would be set up. Here's your density function, k times the square root of x squared plus y squared dy dx. As you go from 0, y would go from 0 to the circle, which is square root of 9 minus x squared, and then the x goes from 0 to 3. Well, this integral is obviously terrible, and we don't want to do it this way. So this, as I mentioned right there, so we're going to go polar coordinates. And we have a quarter circle with radius 3. So being a circular region, that means r is constant. It's not a function of theta. It's just 0 to 3, and quarter circle would be 0 to pi over 2. Now the square root of x squared plus y squared is just r, because if x squared plus y squared equals r squared, when you square root the x squared plus y squared, you square root the r squared, that gives you r. Then of course we have the r dr d theta that always goes there. So there's an r from the radical and an r that must automatically be there. So we will integrate r squared. The first time will give me 1/3 r cubed, which I'll bring the 1/3 to the outside. And the k, of course, which is just a constant. And from 0 to 3, 3 cubed is 27, not 9. The 9 is coming from 1/3 times that 27. So it's 9k, integral of d theta, which is easy enough, that's just theta. So from 0 to pi over 2, that just puts a pi over 2 in there. So we have 9 pi over 2k. That is the mass. Now the my moment, remember we have to put the x in there for that, but keep in mind if you're in polar coordinates, everything has to be polar coordinates. So you can't just leave an x sitting there. X has to be converted. So X is essentially r cos theta. And then we're ready, once we do that, we're ready to go for that integral. So we have the k can come outside again. This time, though, we have 3 r's multiplied together. Same 2 that we had before, and now the r that comes with the x. So we're integrating r cubed, which will then give us 1/4. So the 1/4 on the outside, and there's r to the 4th. 3 to the 4th is 81. So that gives me 81k over 4 on the outside from 0 to 2, pi over 2 of cosine. Antiderivative of cosine, of course, is positive sign. So pi over 2 is 0, gives you sine of pi over 2 is 1, sine of 0 is 0, so that just produces a 1. K still there, so you have 81 over 4k as your my moment. Now remember, the mx moment has the y you have to put in there, which of course then needs to be made polar. So once again, you're integrating r cubed because there's 3 r's, so you have 1/4 r to the 4th, and then the k can come to the outside. 3 to the 4th is 81. So just like the last problem, you do end up with 81 over 4k on the outside. The antiderivative of sine of theta is negative cosine of theta. Now I use that property of definite integrals just to get rid of that negative. I reverse the limits of integration right here. Cos of 0 is 1. Cos of pi over 2 is 0. So we end up with exactly the same moment for this one, 81 over 4k. And now our center of mass, aka centroid. We had 9 pi over 2k as the mass, and both these moments happen to be the same. That's not a typo. 81 over 4k, the k's cancel, flip the 2 over 9 pi. So we have 9 divided by 2 pi, which is 9 divided by a little more than 6. I'm going to say it's somewhere around the 1.4 neighborhood. I could open up a calculator, but it's not necessary. So it's the same 1.4, 1.4, but that would be close enough. Let's say I won't permanently mark it, but I'll just leave it sitting right, maybe right in there, somewhere right about that is a good spot for our center of mass. And that will end this section.